So in today's discussion session, we are going to discuss about the conserved quantity associated with the action or the Lagrangian which we have written for fields, and there are conserved operators corresponding to those if we demand it to be true at the quantum level as well. So we learn about what are the conserved quantity at least at the classical levels first, corresponding to the Lagrangian choice, and then we will see what are the corresponding Hamiltonian corresponding quantum operators related to those symmetries. Okay, so let us recall in classical mechanics, the statement was if I had a system whose Lagrangian was given in terms of q, its time derivative, and let us say maybe a dependency, explicit dependency on t, then the following statement in the term of Noether's theorem was true, that if the q is changed to some q primed such that the Lagrangian does not change, then there is a conserved quantity corresponding to this transformation. A typical example would be if I do a translation x going to x plus a, and if the Lagrangian does not change at all such that it has either a constant potential throughout or no potential at least at all, in those cases Lagrangian does not change at all, then there is a conserved quantity corresponding to this symmetry transformation which is called translation. And we know from our analysis of classical mechanics, momentum is the quantity which will be conserved if Lagrangian has this symmetry. Similarly, if the Lagrangian has a symmetry under time translation, if the Lagrangian has a symmetry under time translation, there is again a conserved quantity corresponding to it, which is the Hamiltonian or the energy. So this logic which we have learned previously, if under certain transformation the Lagrangian does not change or it changes only by a total derivative term, let us say, so a total derivative of some function which is a function of q, let us say, then we know under variational approach these kind of terms do not change your equations of motion. So the idea is I want either it f to be 0 or delta L to be time derivative of some function f. If my change of q generates change in Lagrangian of this kind, then I know there is a conserved quantity corresponding to this transformation. This is what we have learned at the classical mechanics level. Now we want to generalize that statement to field theoretic level as well. So first we will do classical analysis and then we will see what kind of quantum operators get generated out of it. So in analogy to q going to q prime, first we will change things from Lagrangian to Lagrangian density, which depends on phi, and it's all derivative, not just on time. And right now we are not going to put any explicit dependency on either position or time. All the position and time dependency come through the dependency of position and time in phi. So there is no direct dependency of Lagrangian density on x and t. All the dependency on x and t come via phi and its derivatives. So the statement we are proposing that just like q going to q primed, phi goes to phi primed and x goes to x primed. So I'm doing a transformation x going to x primed such that the functional form of phi goes to functional form of phi primed. A toy example would be, let us think of a function of phi in coordinate x which was x square. Its plot would be something like this. Now I do a translation, so x prime which is just x minus a. Okay, in that case in the new phi primed coordinate system or x prime coordinate system, the plot would look like slightly shifted. This will be 0 of x prime coordinate and this was a 0 of x coordinate. This is a function phi primed and this is a function of phi. So you see phi primed of x primed is just the same thing, is just x primed plus a whole square. So you see not only coordinate has changed, x primed and x are not the same thing. Similarly, x square and x prime plus a whole square is not the same thing. So functional form also changes. So we have twofold changes. Once a change in position or position coordinate, and then a functional structure of the function also changes. And in general, at the same coordinate value, the two functions will not be the same. At same physical point, they will be the same. For example, this is a physical point. Its coordinate value is 0 in one frame and its coordinate value is a in another frame. So this is the physical point. But it is not true that phi primed at x primed is equal to 0 is same as phi at x is equal to 0. So therefore, in general, at the same coordinate value, the two functions will not agree to each other. There will be some difference between these two at the same coordinate value. And that difference we are going to write as alpha times delta phi. Alpha is just a bookkeeping parameter like perturbation theory which we have done. Delta phi is essentially the change between the two functions at a given coordinate value x. Now, if we want to keep this transformation as a symmetry transformation, we want that under this transformation of the field, the Lagrangian should change at most by such an element that the equations of motion do not change. That in the phi primed, we get the same equations of motion as we were getting in the frame with x and phi. This is the similar thing which we did here, that q going to q prime, the equations of motion in q prime should be the same as the equations of motion when written in terms of q. So there it was clear that if I had a Lagrangian which involved only a derivative with respect to time, such that the total action was dt integral of L, then the Lagrangian was allowed to change at most by a total derivative of some function of q. In case of field theory, the same analogy if you want to track, the Lagrangian, the action this time is not just the time integral over Lagrangian density, it is the four-dimensional integration over the Lagrangian density. And in order to go to the boundary of this integral, Lagrangian should change by a divergence term. If the Lagrangian changes by a divergence term, that means the total change in the action will be just some alpha times del mu j mu. Now use the divergence theorem, that will be equal to the surface integral times j. So if the Lagrangian density changes by a divergence term, I know the action will change at most by a boundary term. And if on the boundary the field values are fixed, this boundary term will be under variation will vanish, and therefore equations of motion would not change. So the analog of the classical mechanical system where the Lagrangian was allowed to change only up to total derivative, now we have a case that the Lagrangian density might change by a total divergence term. And this will give rise to the same equations of motion, because using divergence theorem we can prove that the variation of action would not change, because at boundary we have kept things fixed. Okay, so in this case we can view the total change in the Lagrangian density to be a divergence term. If it is a symmetry transformation, then the change in phi by this much amount, remember we had gone to phi from phi to phi prime, and phi prime at the same location, same coordinate value x was previous phi plus some difference term. So that's what we have written in the new frame or new coordinate system x primed. This would be the new field structure, previous field plus some other field, and similarly the derivative will be previous derivative plus some other derivative. Now again, as we are doing infinitesimal transformation, as we discussed, this alpha is going to be very small parameter, bookkeeping parameter, so we can do a Taylor expansion around the previous field value, field configuration and its derivative. This is a function of two variable kind of thing, and I have done some changes in both of them. So I can do the Taylor expansion around phi and del mu phi. I will have a first order term in the change in phi like this, and a first order term in change in the derivative of phi like that. Okay, so this would be the total change of the Lagrangian, which we want to be a divergence of some vector. So first we are trying to ascertain what should be the form of the Lagrangian density change, and that we should argue that better that should be a divergence of some term. Okay, so we have this change in the Lagrangian, therefore Lagrangian density will be, therefore this was the previous Lagrangian, so the difference will be this two terms over here. Some alpha is a bookkeeping parameter as we have discussed. So I will just pull out a alpha, and total change in the Lagrangian density will be the two terms which we had written. Now we can do the same trick which we had done previously, that the second term over here which has a the derivative of some alpha times delta phi, okay, that I can convert as, so we have a del L of del times del mu phi times del mu of alpha I had pulled out, so I'm just going to write delta phi. This can be written as a del mu of the whole term, this times delta phi, which is del L upon del of del mu phi delta phi, minus the derivative acting on this term, del mu of del L upon del of del mu phi, and then del phi just getting multiplied. Okay, so this is what we had written. The second term, which is, so the first term which is del mu times this object is written over here, and the second term with a minus sign is written over here, and this del L upon del phi was already present. So I had just restructured the two terms using the total derivative conversion into this form. Okay, so you see, one we have doing that, we have generated the total Lagrangian density, the change in the total Lagrangian density to be made up of the total derivative of something and something times delta phi. All right, and again, if I go to the action, do this action is d4x of L delta L, the change in the action will automatically project this on the boundary, and on the boundary the field configuration, change in field configuration is 0, so this will vanish. On the boundary this will go away, only this term will survive, and that term we also want to be proportional to some j mu. This already is proportional to some j mu. This can be thought of a j mu vector, so it is already a divergence kind of term, so this will not bother you. This term is not clear that whether it is total divergence of something or not, but if we want it to be a symmetry transformation, we should note that it should be equal to some divergence of some j mu. If we force this demand, then what we have, I can bring this term into this side, and we will have equation like that, and the whole thing can be defined as j mu. The whole thing can be defined as j mu. Okay, so now this should be 0. If you see that, if I demand that to be total divergence, that means the divergence of this minus that is 0, which I am writing a small j mu vector. So the small j mu is the term which was surviving and minus some j mu which we want it to be. Okay, so that is a conserved quantity. The small j mu is a conserved quantity. So if I know what is capital J mu, if I can cast it into a form of capital J mu, I will know automatically what is the protected quantity. So you see, divergence of J mu is 0. Previously we wanted the Lagrangian to be divergence full itself, the change in the Lagrangian density to be a total divergence itself. The cost of having that is automatically that this combination is protected. That means its temporal derivative plus a spatial derivative added together is 0. This is like a flux conservation, if you remember, that the time derivative of something plus divergence of some spatial derivative is 0. That means a quantity whose temporal structure is changing in time is equal to the flux going out of the boundary. So some conservation law emerges out automatically if we force it to be a total divergence kind of term. Let us see it via an example. That let us think of a most simple Lagrangian which we have discussed till now. That Lagrangian is just kinetic term, del mu phi, no potential. And let us do a shift of a scalar. The transformation which we are looking for is a shift of a scalar. That phi, all the scalar, the scalar field will change by this constant alpha. If I change phi by this much amount. This is my delta phi, meaning delta phi is hiding here, delta phi is 1. So if I change my scalar field by a constant, then you can see that the Lagrangian structure is such that the Lagrangian does not change at all. So delta L is 0. Okay. So that is what it has automatically emerged out. And therefore, what we have over here, so what we have over here, that small j mu was supposed to be this, the derivative of this with respect to delta phi, which was 1 minus j mu. J mu was the total change in the Lagrangian density itself. That total change in the Lagrangian density has turned out to be 0 in this case. That means capital J mu is 0. So that means small j mu, which is going to survive, was this first quantity itself. Delta phi is 1 and we have to compute this derivative. J mu has been set to 0 because for this example Lagrangian has not changed, or we can say that it has changed by a vector 0, divergence of a vector which is 0. So therefore we have a divergence-less vector which has changed the Lagrangian density. So therefore the small j mu which will be conserved will be del mu phi. Okay, so that means this small j mu, which is also this del mu phi, is 0. So this is way we will do. First we will formally find out what is the change in the Lagrangian. That would be equal to this term alpha times delta L, and this we will try to equate it to some j mu, divergence of some j mu, and then we will compute this quantity explicitly, Lagrangian density change with respect to del mu phi multiplied with del phi, and the difference of this and that is a protected quantity. Okay, so let us do one more example to make things clear, and that example will be for space-time translation. So under space-time translation, the 4 space-time coordinate will change by some constant. I am writing it as x mu goes to x prime mu, let us say, which is equal to previous x mu minus some translation vector a mu. This is 4-dimensional translation vector. In time it will change by a0, in spatial direction it will change by a1, a2, a3. Okay, so under this case, how would be the field transform? Field will be phi at x, just like with the x square example, it will go to phi primed of x primed, and that should be equal to phi at x. Remember, at the same physical location the field should agree. So for example, this is a physical location. In another coordinate system it was written as this, but physical location was this. So its coordinate value was a in one frame and 0 in another frame. So phi at 0 in the previous frame should be equal to phi primed at a in the new frame. So therefore at the same physical location they should agree. Same coordinate locations they would not agree, as we had seen previously. So this is true for translation. That means phi primed at the location x is equal to phi x plus a. From this identity you can put, since x primed, if I put x primed is equal to x, that means x, meaning some value, let us say y, then x would be x primed plus a, which is y plus a. So that means phi primed at y is equal to phi of y plus a. I'm just calling y as x. Okay, some variable. So under this, phi will go to phi primed, whose functional forms are related from its previous version, like this. Again, since for infinitesimal transformation I can do a Taylor expansion, I would write down phi x plus a as the previous function phi plus some difference which will just be a Taylor expansion term, a mu plus del mu phi. All right, this is true for any scalar which is function of x should do that. And similarly the Lagrangian. So Lagrangian is also ultimately is a function on position space x, so it should also change by the similar kind of thing where we had written the total derivative of the scalar times a mu, total derivative of scalar times a mu. Since a mu is a constant, it does not depend from point to point, I can take this inside. Okay, so this is the change in the Lagrangian. Remember, this was the delta L which we talked about, which should better be a divergence of certain vector if it is a symmetry transformation. So that means whatever it has appeared over here, delta L, should be equal to some a mu times del mu, or some parameter alpha times del mu j mu. That is what we have demanded. Now, since there are 4 symmetry transformation, 1 in time and 3 in space, you can think of only time translation, then only A0 will survive, A1, A2, A3 will be 0, or only a x directional translation, then A1 will be non-zero, all others will be 0. So there are 4 symmetry transformation, A0, A1, A2, A3, and corresponding to all of them, I want my Lagrangian to have some J1, J2, J0, J1, J2, J3, del mu of J2 mu and del mu of J3 mu. Okay, so you see, I can write the total change as a summation of all these total divergence terms. Now you can see that comparing this, which has changed, the total change in the Lagrangian is del mu of A mu L, and I wanted it to be equal to some del mu j mu. So that means it is already giving you a hint over what is appearing over here. That is your j mu ultimately appearing for each mu over here. So this is just a reflection will tell you that quantity, which is a Kronecker delta mu nu times the Lagrangian density, should be your j mu. What I am proposing, if I call this quantity as j mu, then you can see that the Lagrangian has changed by del mu j mu. For this j mu, which is written over here, the total change in the Lagrangian, which is over in this circled quantity, is nothing but divergence of this j mu. Okay, so I have identified the piece which can be written as a divergence of total divergence of a vector quantity, which is the total change in the Lagrangian. And if it is a symmetry transformation, it should better be equal to the indirect change in the Lagrangian, which is supposed to come through change in the scalars. Remember, for a symmetry transformation, these two quantities, the indirect change should be equal to the total change in the Lagrangian, which is the total divergence of a vector. So therefore, the same thing I do, the total change in the Lagrangian corresponding to the 4 transformation, A0, A1, A2, A3, you can do one by one, or you can do it together, that under total changes of all this, I would have a conserved quantity called small j mu, which is this quantity. Okay, what have we done? We did not do only one translation, it is 4 translations packet, one along the temporal directions and 3 along the spatial directions. And if I demand a symmetry transformation, this to be a symmetry transformation for the Lagrangian density, the implicit change in the Lagrangian through its dependency on phi should better be equal to divergence of some vector, and that vector we have identified is this j mu. This nu over here is getting summed over. This means summation over nu. Similarly, the nu over here is also summed over. So we have identified, looking at the total change in the Lagrangian and looking at the total change in the field, what should be the capital j mu, and then we have found out what should be the total j mu, small j mu, which is a conserved quantity. The form of the small j mu which has emerged out of it has this structure, that there are 4 quantities, 4 symmetry transformations, so corresponding to each there should be a conserved quantity. So therefore there is a 4 parameter A0, A1, A2, A3, and corresponding to each nu there is a unique j mu, just like J0 of mu, J1 of mu, J2 of mu, and J3 of mu. Collectively it is called T mu nu. Nu, the lower nu tells you which translation you are talking about, spatial translation or temporal translation, X translation or Y translation, and the upper T mu change tells you the 4-dimensional vector corresponding to that nu. For only temporal transformation, only A0 will survive and all other A1, A2, A3 will be 0. So nu will survive with value 0 over here, and it has a vector now, T mu 0. Mu will take value 0, 1, 2, 3. Similarly, if only x directional translation you are talking about, only A1 will survive, all other A0, A2, A3 will be 0. So I will have a T mu of 1, and mu can take 4 values. So there are 4 dimensional vectors for each lower index. So therefore I have a 2 index quantity together which I can write, which is T mu nu. And look at this structure. This is the full T mu nu which we are talking about. This whole quantity is written like this. This is an elementary exercise for you to prove that the T mu nu which I am talking about is just this. Your exercise is to verify that given this definitions of T mu nu, the total small j mu which I have written upstairs is just with this T mu nu, the total j mu is this. That you can verify. So there are four-dimensional vectors: j mu, j0 mu, j1 mu, j2 mu, j3 mu. Collectively, I'm calling it T mu nu. This T mu nu is given a name. It is called energy momentum tensor. Why energy momentum tensor? It will be clear in a minute. But these are the 4 quantities. Actually, you can see that for 4 translations, temporal translation, energy is conserved. 3 spatial translations, momentums are conserved. So therefore, it is called energy and momentum tensor. 1 index will talk about energy and 3 indices will talk about momentum. So let us see it explicitly. For example, as we kept discussing, let us think of only temporal transformation, temporal translation. So A0 is going to be 1. All other quantities of translation parameters are 0. So under this case, I know only one of the element A0 is non-zero, and similarly here also only one of the element A0 will be surviving. All other quantities will become 0 because alpha 1, alpha 2, alpha 3, which is actually A1, A2, A3, they are 0. So only thing which will be surviving will be A0 times del mu J mu 0. So that is what it is surviving. J mu 0, effectively the 2 index object we are going to call T, not a J. So T mu 0 will be surviving. That is the conserved quantity, the capital J mu corresponding to that. Okay. So the capital J mu is which the stress energy tensor which is of relevance for us is T mu 0. Now let us see what is the conserved quantity corresponding to, meaning the conserved quantity small j mu is this T00. This T00 is, remember, there is this term and there is this Lagrangian term which is coming about here. This was the capital J mu. This has become the small j mu completely, which has it has got 4 different values corresponding to different mu. We are just selecting it for one particular A0 is equal to 1, rest of them are 0. So that means we have focused on T mu 0 kind of things. What are its component? Its components are T00, and then J1, small j1 will be T10, small j2 will be T20, and small j3 will be T30. So just first focus on what is J0, which is T00. T00 from this definition will be del L upon del of del 0 phi. Sorry, here should be del of del 0 phi times del 0 phi, because mu and nu both have to be 0, and right hand side the second term will be delta 00, the Lagrangian density. Remember this quantity over here, we have seen it before. That was the conjugate momenta pi. So I have a pi times del 0 phi minus the Lagrangian density coming from here, which we know by now is just the name of the Hamiltonian. So you see, if I have a only time translation for the Lagrangian which we had written down, the Lagrangian was just del mu phi, let us say. For that Lagrangian, I would have a quantity which is energy, total Hamiltonian. Or actually, for this case, we do not have to specify what is the Lagrangian. Only thing, its kinetic term should be del mu phi, del mu phi. If the Lagrangian density has any structure minus v of phi as well, then also this statement will go through. that you have this object first derivative times del 0 phi is pi times del 0 phi, and this Lagrangian will involve phi as well. But still, T00 will be the Hamiltonian. So therefore, under time translation, a conserved quantity is present in the field theory picture as well, which is Hamiltonian. Remember, this is classical field theory yet. We have not quantized anything as of now. Okay, you can try to find out what are the Ti0, that means T10, T20, T30. This is an exercise for you, and I'm just giving you the formula which you have to obtain. You will just get del L of del I phi and then delta I0 L. This will vanish because Kronecker delta survives only for delta 0, 0. So only the first term will remain. And for a given Lagrangian, you should be tempted to find out what is that a conserved quantity which we are talking about. Okay, so just do this exercise and you will find out that Ti0 is del I phi del 0 phi and the quantum operator corresponding to that. Now you can make all these things as quantum operators. But anyway, that is not very relevant as of now. Quantization we can do. We know how to do quantizations. All the phi's and pi's will be converted into operators. But first we are looking for their structure. So there are conserved quantity J mu whose components are Ti0 and T00. T00 we have identified as the Hamiltonian density. Ti0 is not quite something which we have seen before, but it is something like a flux. Remember, T mu 0 is supposed to satisfy this quantity, this equation. That is to say, del 0 of T00 should be equal to del I of Ti0. So this is the flux of something being carried out. This has this structure. Remember, del T of something plus divergence of something else is equal to 0. That means this quantity's rate of change is equal to minus of the divergence of spatial divergence of something. That means this is a flux conservation equation. So this is some sort of a flux. Ti0 is some sort of a flux which we are talking about. Okay, so this is the structure which would emerge if I demanded only the temporal translation. Similarly, if I do the spatial translation along, let us say, one direction, so this should be 1. So that means A1, let us say along the x direction we are talking, the spatial translation. That means A1 will be 1 and all other A0, A2 and A3 will be 0. In this case, the conserved quantity small j mu will be T mu of 1. Remember, the nu was talking about which direction translation we are talking about. If we are talking nu is equal to 1 is surviving, all other nu's a nu is 0, then only one quantity will survive, which is T mu 1. So your conserved quantity is T mu 1. Again, you can find out it has 4 components: T01, T21, T11, T21 and T31. Okay, so the 0th component of that is T01. Look at the definitions of T mu nu which we had given above. You have to put 0 and 1. This nu should be 0 and mu should be 1, and you will get this quantity over here. This is T mu 1. Okay, sorry, it should have been the other way. This should be mu. No, that is fine. This should be mu was supposed to take value 0, so here it is 0, and nu was supposed to take value 1, which is over here, and this will become 0 because of a Kronecker delta function. So we will get del 0 phi del I phi, which is this. Okay, which up del 0 phi can be converted into lower del 0 phi with a minus sign. Remember, del mu of some function is equal to eta mu nu, where summation over nu is implied, of del upper mu of f. So del lower mu of phi is eta 0, 0 of del 0 phi, upper phi. So therefore I have a minus sign. So remember, this del 0 phi was again a pi, and this del 1 phi I am just writing as del 1 phi. So if we are insistent on calling the conserved quantity along due to the spatial translation as a momentum, then the momentum which we have obtained over here is this. This is the definition of momentum. There has to be a c parameter which is coming along because of the unit c is, I'm working in unit c is equal to 1 as we had discussed previously. But ultimately you would have this definition of momentum. This is the conserved current. This is the conserved current which is conserved quantity which is present due to symmetry along space translation. Previously we obtained the Hamiltonian was a conserved quantity, del 0 was a conserved quantity. So just to write one thing, if you get something like del mu j mu, some j mu is equal to 0, this is equal to del 0 of j0 plus divergence of j, small j, is equal to 0. If I do the d3x integral of the whole equation, so then I will have a del 0 which is time derivative d3x of j0 plus, or let us take it on the right hand side. This is minus of d3x divergence of j. Again use Gauss's divergence theorem. It will project you at the boundary of this volume which is at infinity. That is j dot ds at r tending to infinity. And if the j has the structure that it vanishes at infinity, right hand side becomes 0. That means the integral of j0 does not change in time. Its temporal derivative is 0. So that's why t00 integral over d3x will be a conserved quantity. That is the total Hamiltonian. Similarly, for spatial translation, the j0 which is t01, its integration over d3x will be a conserved quantity in time. That will be the momentum, and the momentum therefore will be the d3x of this j0. Okay, so pi times del I phi d3x is the quantity which can be called as a conserved quantity corresponding to spatial translation, and therefore it is the momentum which we identify as a symmetry, the conserved quantity corresponding to space translation symmetry. Okay, lastly, to look at how this operator looks in the quantum domain. For example, corresponding to time translation, the conserved quantity was the Hamiltonian, which was integration of t00 over the spatial volume d3x. The Hamiltonian operator we all have already seen in the previous classes, that it would be just a dagger a times h bar omega plus half delta 0. That was the Hamiltonian for scalar field of the Lagrangian which we had written before. Now we have landed up with a new operator which is this new conserved quantity which is this. So I know how to write phi in terms of the a and a dagger, and I know how to write pi in terms of a and a dagger. So let us use that and write down those two quantities. Remember, the phi and pi both will come with the integral quantity d3k prime, one for phi and one for pi. The spatial derivative is of phi has to be taken. That will throw up iota times ki. So this will give me a ki prime. So I'm writing phi as integration d3k primed upon root 2 omega k primed and a dagger. So if I do that, I would get iota over here times ki after the taking the spatial gradient operator. If I do the spatial gradient operator, I would get a iota k. Okay, and then the pi I have to write down the just a second. So there should be iota over here. The pi I have to write down. The pi would be just omega k upon ic times this quantity a minus a dagger. So remember, when I take the gradient of phi, This part will give me e to the power plus iota k, and this part will give me minus iota k. So there will be a relative sign difference. So both the terms phi and delta gradient of phi, pi and gradient of phi, both of them will have this structure, a relative sign between a and a dagger. So this is simple algebra. You should try it doing once. Write down what is phi and write down what is gradient of, write down what is pi and write down what is the gradient of phi, and you will get this kind of structure. Okay, so you do the algebra slightly carefully. You will find out that the d3x of that has to be done, because remember the momentum, which is a conserved quantity which does not change in time, is rather d3x of the t01. Okay, so that spatial integral has to be done. That spatial integral, so there is a x dependency here, there is x dependency here, here. So you will have a product terms. This will multiply among, this will multiply to this will multiply to that, this will multiply to the first term, this will multiply to the second term. There will be four different multiplications. So I have written four different multiplication terms over here. All of them will have some exponential times k plus k prime dot x or k minus k prime dot x and so on. And there is a d3x integral which is just over here. Again, I will just urge you to do it slightly more carefully than what I'm giving here. You can just verify whatever I'm going to write over here, whether you get it or not. So you will have spatial integral I'm going to do first, and the spatial dependency is only in the exponential functions here, here and here. And all of this integration are going to give me either of Dirac delta of k plus k prime or k minus k prime. You can see the structure. This will give you k plus k prime, this will give you k minus k prime, this will give you k minus k prime, and this will give you k plus k prime. So it would be either equal to k plus k primed or k minus k primed. And remember the identity which we had previously, that a of minus k is equal to ak dagger for real scalar field. Use those identity as well, and you will get this kind of operator at your hand directly. And here you will see that you have a structure which is these integrals over here, which are surviving over after doing the simplification, they will just vanish because of odd integral structure. These integrations, these parts are symmetric under k going to minus k, while this is odd function, this will vanish. But for these two terms, they will not vanish under integral, and these will survive. And you can figure out that the momentum integral, the momentum operator which you are talking about, is just this operator, ak dagger ak times ki. Remember, this was omega, h bar omega. If it had been, it would have become the Hamiltonian operator, but this is not h bar omega, so it is h bar ki. Okay, so in this case, again, you can see that this is a vector component, x component or y component or z component, depending upon I. This is symmetric under k going to minus k. So again, the second part of this integral will vanish, only the first part will survive. This is not symmetric under k going to minus k. So therefore, ultimately, this appears for a while, but under integration vanishes. So at the end of the day, you are left with pi upon c is equal to h bar upon c times this. So that tells you that momentum operator pi is equal to h bar times this integral d3k and then ki, the ith component, forget about the vector sign, ith component of momenta is ak dagger ak. It just counts how many excitations are there in which mode and associates a momenta h bar k to that mode and sums over all the modes. This is how you calculate the momentum of a field. Total momentum of a field operator is this. Take its expectation in vacuum state, you will find out that is 0. Take its expectation in 1 k naught state, you will find out that it is h bar k0's ith component. This is an exercise for you. You can verify that it only counts about what is the mode present, which mode is present, how many of them, and associates those many ki's to it. In this state, only one excitation is present in k naught mode, and therefore it gives you h bar k naught I. So therefore, this is the momentum operator which we will get after doing this computation in different states. Okay. So I wrap up the discussion on the scalar field and expectation. In the cases when we start dealing about interactions of atom with fields, we will see more examples of what kind of operators naturally appear. But now we are familiar with how to convert those operators in terms of AK and AK dagger, what are the conserved quantities. Using those, we will compute things in later classes. So I wrap up the discussion on the scalar field here. I will just briefly introduce the Dirac field structure, which is very similar to this, and light, which is electromagnetic field structure, which is also close by, in a couple of lectures coming from the next discussion session onwards, to just give you complete glimpse of what kind of fields are present in nature and their structure. One has to be slightly careful about it, their spinorial structure or vector structure, but more or less central physics will revolve around this, that you have to correctly identify what is the field operator and what are the other relevant operators which can be made from the field operators. Okay, so we will see those things coming up for Dirac fields in the next class onwards, and later on for electromagnetic field. All right.